All right, good morning. Any questions on homework 1? So there was one question that I received that I think was a good question. So on question 3, so remember, so we did go over a very similar question in class. And it's very important that for every single transition that happens here, that you're very careful looking at every single possible wire and checking like, okay, like was there ever a glitch there? Like keep very careful attention to exactly what time each wire flips, because remember that wire is going to be fed into the next gate, and then so all the glitches will propagate until eventually maybe if you have like a gate that cancels out whatever is received. So like if you have like a 0 passed into an AND gate, then it doesn't matter what the other input will be. Or if you have like a 1 passed into an OR gate, it doesn't matter what the other input will be. But everything else, you need to make sure that you propagate all of the hazards very carefully. So make sure, maybe try chatting with a friend, try to make sure that you really match with all the other students around you in your study group. This is kind of a confusing question. It will be on your midterm, which is in about 2 weeks, 3 weeks, 2.5 weeks. So get excited for that. So make sure that you really try to understand this question. I think this will be probably the hardest question on the homework. Last quarter, I think like 30% of the class got this question correct on the homework, and then proceeded to receive 30% as well on the midterm. So anyways, okay, just stressing that this is a hard question. So spend a lot of time on it. Another thing is it is possible that you could actually receive 0 as an answer, to where you realize that you pass through and it's like, oh, actually like nothing changed and the outputs are still exactly the same and there were no glitches. So in the case that there are no glitches and the outputs stay consistent, then in that case, the delay, we would say that the delay through the circuit would be 0 nanoseconds. So that is possible. I don't remember if that is actually one of the answers for one of these guys. So just double check with your friends. But yeah, just wanted to throw that out. Yes, question?
For the delay, do we put it for like the total circuit or one for Y1 and Y0?
So the question says, I guess it does leave it a little bit vague. I was assuming that you would take the max of these two. So whichever one takes longer, that is what I would say is the delay of this circuit. But yes, I would also recommend just writing both, just for your own sake. Question?
Is the second output on D non-zero?
Yes, you know what? That's so interesting. I thought I updated this PDF to fix that. But I just downloaded this and it's wrong. So actually, yeah, okay, it's good announcement time. I believe that D. What was the correct transition for this, or the correct value for this? Was it 0, 1?
Yeah, I think it's 0, 1.
Yeah. Okay. So sorry about that. I thought I fixed it. Turns out I did not. So yes. How do I feel like? Wasn't there? How do I? These updates, oh my goodness. Okay, well, that's okay. 0, 1, that's what these values are supposed to be right here. Yes, okay. Maybe make a note of that, write it down in your homework. It's supposed to be 0, 1. Okay, well, that was exciting. Okay, good. Yeah, that should fix that part. Any other questions? Any question on would you like me to go over any of these questions? Yes?
I had a question about the timing one, the one you were just talking about.
Okay.
For part C.
Yes.
So, if you look at wire A, it switches from a 0 to a 1.
Yes.
And in the previous state, like the original state,
Uh-huh.
if you look at the AND gate on the top,
Yeah.
the lower input is green. Like, if you propagate through to the previous state.
Okay.
So I'm wondering if when it turns to a 1, if like the 3 nanoseconds for that AND gate will happen immediately, like at the same time as the AND gate down to the bottom, and then if the Y1 would turn to a 1 and then later turn back to a 0.
Sure. Good question. So if you have the case, let's assume that you have the case where starting out, you let me draw it in red. So assume starting out you have a 0 stored in this wire, and assume that you have a 1 stored in this bottom wire. So at like time equals 0, we have 0 and 1. What will the output of this AND gate be?
Like, I'm wondering if,
But yeah, so I'm gonna go through it, kind of slowly right now. But what is the output right now at time equals 0 if we have this operation? What is it? Say it. 0. Yeah. Okay. Thank you. Good. Okay. Good. So this is steady state. Yeah. Now if we have the condition where maybe somewhere over here we have something changing, and maybe after like it takes a while to propagate. So maybe it takes 11 nanoseconds to propagate all the way through. So maybe at time equals 11, now this switches to 0. Okay. Versus up here, well, let's assume that, at time equals maybe 0 immediately, this now changes to 1. Okay. So that means that for a little bit, we're actually going to have 1 and 1. And how long are we going to have 1 and 1 active on this AND gate? Yeah, for 11 whole nanoseconds. Yeah. So there's an 11 nanosecond period where we are receiving 1 and 1. So now that will come into this AND gate right here. And so how long does it take to transition from 0 to 1? Zero to 1. Yeah.
14 nanoseconds?
Ooh, so not quite. So to transition from 0 to 1, remember, so we have this glitch where we have 1 and 1. This will happen at 3 nanoseconds. Because at time equals 0, maybe it changed from 0 to 1. So now at time equals 0, we have 1 and 1. And that means that now it takes 3 nanoseconds for that change to propagate. So now we have 0 changed to 1 after 3 nanoseconds. But then, yes, after that, then it changes back to 0. And what time does that happen at?
14?
At 14, yes, exactly. Yeah, does that make sense? Sure, yeah. So, yeah.
12 and 15 actually. Because there's a 1 for the not.
I just pulled out this number out of nowhere.
Okay.
I created this. Yeah, sure. So the actual answer could be different. Yeah, kind of makes sense. So in this case, there was a hazard, and how long did this hazard last for?
11.
Yeah, that lasted for 11. This 1 should not have happened. It should have stayed 0 for the full time because we transitioned from like the output of 0 to the output of 0. But we actually got a 1 for like a full 11 nanoseconds. Yeah. So okay. So yeah, that is a possible example of what could happen for C, I guess, if you actually did have a 1 transitioning to a 0 here. I don't remember exactly what happens. Okay. Good. Is there another question you'd like me to go over? Yeah. What about, does question 9 make sense? So, have we started the homework? So question 9 is using like lookup tables and talking about PDKs and muxes and things. Did we have a chance to read through this? It's a little bit confusing. We can also talk about it on Monday. Yeah, question.
Do you think you should talk more about part C on 9?
Part C on 9. Yes. Sure. So, okay. So what this question is effectively asking is we have this Verilog right here. Assign y equals a plus b. Okay. And we are being asked to implement this y value using each of these like different steps. So the first step is saying implement this using a PDK with only full adders, and then part B is PDK with only 2 input muxes, and part C is a Xilinx FPGA with only 4 input lookup tables. What is a PDK? Yeah.
Process design
Yeah, exactly. Thank you. Process design kit. This is just a set of standard cells that your foundry will grant you access to. So if you're going through, TSMC, Intel, Micron, whatever foundry is creating your chip for you, they will give you access to a PDK, and they say, hey, like, we have a PDK that is only full ladders, or we have a PDK that is only 2 input muxes. This is purely educational. PDKs will have thousands of cells for you to choose from. They will this is completely fake, but it simplifies the question. Yes. So, okay. Versus part C is an FPGA. In FPGA, you have a bunch of different standard cells that you also usually have access to. In this case, we're assuming that we only have lookup tables, so you are not allowed to use any of the other standard cells that come with FPGAs. So you have a lookup table. So we can go into the documentation here and remind ourselves what a lookup table is. But if we remember, so I did cover this a few lectures ago, but how do you draw out like the implementation of a lookup table? Like, what is required? Yeah?
I guess just the number of inputs for like what number of lookup table it is, and then just one output, like into a ball.
Sure. Okay. Yeah. So that would be like the like schematic diagram. So yeah, if we have like whatever. So these are the inputs. This is the output. So Y. Okay. Cool. Okay. What is missing from this? What like additional thing do we need to put here? Because remember, so this is a lookup table. So what do we need? What was that? Sure, about 4. So yeah, what do we need now to implement this? Yeah. Exactly, values in the table, right? So this is the first part, is you draw out this circuit thing. So yeah, so maybe you pass in the value of like A and B, and maybe you just like hardwire the other inputs to 0 or something, or you hardwire them to 1. You can do whatever you want, as long as you now fill in the table correctly. So what you will need to do is you'll need to have like A, B, and Y, and probably all of these other inputs as well. So maybe you would have C and D. And so you need to go through all of the 16 possible inputs and assign a value to them. Okay. If this was our structure, okay, then we can probably just leave off the cases where we have like whatever, 0, 0 or something. We can just say like this is, like we don't care about this because we're never going to reach the state anyways. Right? So if you have, whatever. We don't care, we don't care, we don't care, X. We could say like we don't care what A and B are. So X means we don't care what it is. Right. But then if C and D are 1, then all of a sudden we actually do care what A and B are, because remember, so we're filling out this table. We're trying to give this table functionality. Okay. So I don't know what would be. I'll give you this first one. So if A is 0, B is 1, then what do we set Y here?
1.
Yeah, sure, 1. Okay. Cool. So what you'll need to do is just go through this table and fill it out. So in general, when implementing a lookup table, this is actually the most important part, is this table right here. You go through and you assign values to every single output. Yeah. And this is what like Vivado will do for you. It has a bunch of lookup tables that it can assign, and Vivado will automatically fill all of the lookup tables to implement whatever functionality it needs. Yeah, question.
Why do we need C and D?
Because this is a LUT4. So it has 4 inputs, whether we like it or not. So the table is 16 entries long. Yeah. If it was a LUT2, then we wouldn't need them. If it was like a LUT5, then we would need an additional one. Yeah. Makes sense? Yeah.
So in order to bypass the fact that it's a LUT4, 2 of the inputs are always going to be on, no matter what.
What was that again?
So two of the inputs are always going to be on, let's say, C and D to allow you to access A and B, or?
Well, so this is, I just happen to have chosen this. We could actually, if we want, like this, it's completely up to you, as long as the table, correctly matches the circuit that you've implemented. So yeah, if you wanted, you could have it be like 0 and 1. You would just need to change the table accordingly. Or you could have them be open, and then you would need to change the table accordingly. Yeah. Yeah.
What would changing the table accordingly look like?
So what you would do is you would look at the like set of the way that you've connected everything, and the most important thing is you just want to make sure that for every value of A and every value of B, that Y is the correct value.
But like, do we know what the correct value for Y is?
Yeah, it's given to us right here.
Oh, sorry.
Yeah, so we're implementing addition. Notice that it's Y is only 1 bit. So yeah, no Y truncates A plus B to 1 bit. So when we do addition like that and then truncate it, what gate is that actually? Not OR, yeah, it's XOR, right? When you have a 1-bit addition, remember if you think back to like our half adder implementation, the bottommost bit is actually just an XOR gate, and that's it. Yeah. So actually, this right here is actually just asking for an XOR gate. So yeah, think about that. Cool. Question?
So if A and B are both 1, then the output would be 0?
Correct, right, yeah. Because if you have 1 plus 1, then the output should be 2, but we're truncating it to only 1 bit, so it just gets rid of the top bit. Yeah.
Why do C and D matter then?
C and D are the implied inputs into this lookup table. So A, B, C, D. And this is because it is a LUT4, so it must have 4 inputs because that's just the cell that we have access to. I could have asked the question with like a LUT2, and now that would only mean that we would have just 2 inputs. Yeah. Or if it was a LUT6, then now there would now be maybe C, D, E, F on this. But we just need to make sure, the most important part is we just need to make sure that the table is correctly filled out. Yeah. LUT4 means that there are 16 entries.
So does the C and D not matter and it looks up the Y?
Basically, right, yeah. But they matter in a little bit. You just need to like double check, try plugging things in, make sure it all works. Yeah.
If we hard code C and D, do we still need to include all of the options in the table that C or D could be?
Yeah, so the table is 16 entries whether we like it or not. It is 16 entries. So you must fill out every entry. I guess I cheated a little bit here by putting like we don't care what A and B are. Then that's effectively making like this one entry is effectively now 4 entries in one. I'm saying that like for each one, they're all don't cares. As long as you're clear about it, you could explicitly write out if you wanted. You could say like cells not shown in this table we can assume to be 0 or something like that, or we assume to not care something. As long as you explicitly write it out. But yes, the LUT4 table is 16 entries, so you must fill them all in some way. You can fill them verbally if needed. Yeah. Okay. Is this making any more sense? Try to, I don't know, create some study groups. Try to chat with your peers. We can also talk more about it on Monday. Okay. Any other questions on the homework? So this is implementing or drawing out the schematic that is generated by here. So it's saying using full adder and half adder cells. So if we just like quickly look at this. So what width are A and B? 8, yep. And so when you sum them together, what is now the output size? 9, okay. How many full adder cells do we need for this? All right, let me take a step back. How many half adder cells do we need for this?
1.
Yeah, correct. 1. And then how many full adder cells do we need for this?
7.
Sure, yeah. Okay. Oh, look at that. Whoops. That's the answer. Okay. Okay, well, oh, another small typo. I don't know how this happened. This is supposed to be base 10. This, yeah, whatever. Sorry about that. That should be like 0, 0. Like that. Okay. Cool, okay. I'll take a break from this. Please come on Monday with the homework all done so that you can come in and ask questions, and then you'll all get 100% on the homework instead of people last quarter that got like 30% on this question. So yeah, yeah.
I have a question for Sage.
Yeah.
He was talking about the two's complement.
Yes.
Does that mean like, so for, I guess for example, 17,
Yes.
or I mean, yeah, positive 17, does that mean to like change it into binary, then take the two's complement of that, or represent?
So 2's complement is just a representation. So yes, so what you'll need to do is convert this to binary, but it doesn't mean that you need to like negate it. Negation is like a separate operation entirely. So yeah, for like -6 right here. So that's also like, yeah, how do you, oh sure, and it says do it in 8 bits.
So for the negative,
Yeah.
so I guess for like -6, it would start with the 1.
Exactly, yeah, right. It would start with a 1 for -6, and for positive 17, it would start with a 0. That's just definition of 2's complement.
And then same with like E2, when it says to, just like what that represents.
Yeah, right. So given that this is stored, I get, honestly, I guess the wording isn't perfect. Given that this is stored as 2's complement,
Yeah,
give the decimal value.
so that would also be a negative.
Yeah, it'd also be negative. Why would it be negative?
Huh?
Why would it be negative?
For two's complement, if it starts with the 1.
Yeah, exactly, yeah. So this starts with a 1, so therefore we know it's negative. Yeah, question.
So is the positive number in two's complement just that number binary, or is that number complement with 0 at the start?
Ooh,
Like you want it to be complemented, you want it to be flipped and then just have the 0, or and still shift it over? Two's complement, everything's like shifted over.
Right, so in 2's complement, a positive number, yeah, in 2's complement, a positive number is just that number represented in binary, except what do you really need to make sure happens if you have a positive 2's complement number? There should be a, yeah.
Within the range.
Yes, it should be within the range. But most importantly, the most significant bit should be 0. So that is 2's complement. Positive number should have a preceding 0. The negative number should have preceding 1. Yeah, maybe write that down. Double check it. Okay. Cool. Okay. This I'm not going to spend a bunch of time on this because I think you've all kind of learned this, but it's very important in like every single thing that we're going to do in this class, especially with what I have planned for the rest of class today. Yeah, last minute question? Yeah.
I was just gonna say the lower
Number 4? Sure, so I kind of went over lookup tables already a little bit. So, yeah, so given a 2-input LUT, so these are the different addresses that can go into that LUT. So what is the size of the table of a 2-input LUT? Yeah, it's 4. You can store four possible things. So it's saying, assuming that, yeah, we have these 4 cells, just go and fill them out in order to make an OR gate. And similarly for this, now assuming that we have a 3-input LUT, how many inputs, how large is the table of a LUT 3? How long is the table? Yeah, 8, I think someone said it, right? So there are 8 possible entries because it's a 3-bit address, it's a LUT 3. Okay. And then, okay, so for a 2-input LUT, so remember, so there's the table size is 4. Okay. what should the, so if the table size is 4, then how many possible ways could you fill that 4-element table? Yeah, 2 to the 4, which, yeah, I believe is 16, right? Okay, so then you could probably extrapolate that out for the k input level. Okay, cool. Okay, I'm going to move on. Hopefully it's all good. Okay, excellent. Give me just 1 second. All right, we're entering a whole new unit. Hope you're all super excited. Does anyone know what this symbol is? Yeah?
Is it like a flip-flop?
Yeah, this is a flip-flop. That's correct. What is a flip-flop? What was that? Yeah, so a flip-flop is a memory storage device. So it stores memory. Specifically, it stores one single bit. And this bit is on the Q side. And yeah, so it can either be 1 or it can be 0. All right, cool. So now we can, boom, stores memory. And we could also store, we could put a bunch of flip-flops all in a line. We could probably represent like larger numbers, not just a 1-bit number. So yeah, so let's say we wanted to store the value like 7. Okay, so if we want to store the value 7, how many flip-flops would we need? Yep. Yeah, you would need 3 flip-flops to represent the value 7. So yeah, if we have whatever, I'm writing 0b to represent binary. So if you have 1, 1, 1, so this is 7. So that means that you now need you need 3 flip-flops. So yeah, so when I put this bus symbol here, that actually means that, yeah, we have like a z-axis. So it's going into the paper. We have a stack of 3 flip-flops here. Okay, cool. So memory, sometimes you want to just store things, but most of the time you probably want some way to update that stored data so that it's, yeah, more useful. Otherwise, it would just be a ROM, similar to the ROM that you were using for your previous lab that you just finished yesterday. So instead of just this being a ROM, there is this D input. And D, I actually don't know the exact source of it. There's a lot of people that think the source of D means like data. Some people think it means delay. So I'm not sure exactly what D stands for. Anyways, so that, yeah, if you can find out like the original source of why we call it D, then I'll be very happy, and then I'll tell people in future quarters. But anyway, so then we have this D input, and so this D input, well, I can pass in a value, and maybe I want to pass in the value like 0, 1, 0. And remember, so this is 3 flip-flops right here, all stacked up on each other. And so I'm trying to feed in this data, but because this is a memory storage device, we're stuck in this. We're not going to update our data. We're not going to update from the input until we receive a signal that tells us, okay, it's time for us to update all the data. And that is this port right here, which is called the clock input. Has anyone heard of clocks in chips before? So maybe you have a CPU and it specifies like the number of hertz that your CPU runs at. Does anyone know like what like a modern processor will run? What clock frequency it runs at? Yeah. Right, yeah, so it's anywhere from, let's say, like 2 to 7 gigahertz. If it's a phone, probably runs a little bit slower just to save power. But if it's like a supercomputer, then yeah, it's running at like 7 gigahertz. And what that means is, so this clock wire is actually routed globally all around your chip and is fed into potentially tens of thousands, hundreds of thousands of flip-flops all around. And so when you buy a CPU and it's like, oh, this runs at 5.7 gigahertz, you're like, wow, that's so cool. It's like, what does that mean? It actually means that on the chip you have tens of thousands of these little cells right here, these memory devices that store something, and there's thousands of them, and the clock is fed into every single one of them, and the clock is specifying how quickly each of the flip-flops will update their data, or how quickly they can update their data. So in like the fastest sense, you could imagine that maybe we have a flip-flop that's changing between like 0 and 1, 0 and 1, 0 and 1, like every single clock cycle. Or you could also imagine that maybe you have a memory device that it's stuck for a very long time until finally, like after whatever, thousands and thousands of cycles, maybe finally someone decides to update the value. Yeah, so memory devices, very cool. Let's see what we can do with them. So maybe the first thing, you know what? I'm going to leave off this. No, I'll leave it. Generally, in circuit diagrams, you generally want to leave off the clock signal just from the schematic, just because it's a little bit like clunky and it's implied by this symbol right here. Anytime you see this symbol, it means that the device has a clock plugged into it. So you actually won't ever see clock like in circuit schematics, but generally it like is there. But I'll leave it there for now. Okay, so let's say we have maybe a black box. Okay, and let's, instead of this storing 3 bits, I'll make a new page actually. So instead of this storing 3 bits, maybe we'll have it store the number 32. And how many bits do we need to store 32? I think it's not quite 5. Yeah, what is it? 5? Oh, I think it's 6, right? Yeah, so it's because we have 5 zeros and then a 1 at the front. So yeah, so anyway, so this is a 6-bit flip-flop, okay? And let's say that this output goes into this black box and then comes out of this black box and then comes back into this input. And maybe let's say that now out of this black box, it now has the value of 16. So maybe it's like it divides it by 2 or something. Okay, cool. So now the data has flown through. So 16 is currently at the input. Remind me, so what triggers the data to switch, to propagate through the flip-flop and now reach the output? What is required? Yeah.
The clock.
Yeah, the clock. Yeah, so specifically a clock pause edge, okay, or positive edge. And that is the idea. So here I have the signals written out. So when you have the clock that oscillates from 0 to 1, it changes from 0 to 1, this is considered a pause edge. And this is the thing that actually signals all flip-flops in the chip. Like every single flip-flop, like, okay, it's time to change. Like now, okay. And then every single flip-flop will update its value and then send that value out now through the combinational circuit. And finally it'll arrive back at the input where it will wait for, what will it wait for? Exactly, the next clock edge. Yeah, so the clock is what powers the flip-flops to change to the next value. And basically, flip-flops are just waiting there all the time, waiting for the next clock edge, then boom, receives a clock edge, and then boom, okay, sends it through the combinational circuit, sends it through, okay, now it's back at the flip-flop, and then it's waiting, and then boom, okay, receives another clock edge, so then the signal goes through. Yeah, so that's how, that's kind of why we've been talking about combinational logic. That is like muxes and gates. That's everything that we've been doing that does not involve a clock. Combinational logic is all of the logic that is sent out of a flip-flop and then into another flip-flop. So that is kind of the piece that we were missing. Everything comes out of flip-flops and then goes into flip-flops. Okay, right? So maybe write that down. So everything that we've been doing in this class so far, we've actually just been assuming just like an implied flip-flop output and an implied flip-flop input. Yeah, on every single circuit. Okay, good, okay. So if we received this pos edge, and let me write this out. So if 32 is currently being stored in Q, then let me put that in this waveform. So Q is currently set to 32, and what is D currently set to? Yeah, D is 16, okay. But then boom, on this pos edge, okay, then what is now the new value of Q? Yeah, 16, right, so it propagates through. So on a pos edge, propagates through. So now this is 16, okay? And immediately after this happens, D is still 16. But now that this Q is outputting 16, then it'll propagate through this wire, go through this black box. And yeah, maybe this is actually like a right shift unit that just divides by 2 every time. So now maybe it comes in through here, divides by 2 again, and so now instead of it being 16, it's divided by 2. So what is the new value of D?
8.
Yeah, sure, so maybe now it's 8. Okay, and then we wait. What are we waiting for? Yeah, for another rising edge, right. So this goes, and boom, now let's say get another rising edge. Okay, let me also write this out. A lot of terms that I'm dropping on you. So positive edge, also called a rising edge. What would we imagine that this is called right here? Falling or negative. Exactly. Yeah. Let me write that out. Falling. What? Okay. Right? Okay. So then, yes, so at this point, then now we receive another pos edge. So what happens to our flip-flop? Yeah, it updates, correct? What's the new value? 8, yep. So it just grabs whatever was on the previous cycle. And now 8 propagates through, divides by 2, is fed into D. What is D now? 4, yep. Okay. And then finally, I don't know, we'll do one more. So we have one more pos edge. So what is Q now? 4, yep. You can see it's just brought over. And then now what is D? 2, yep. Because 4 is propagated through the combinational logic and then fed back into D. Okay. Good, right? Yes?
What happens if the clock is faster or updates faster than the combination?
Ah, fantastic question. That is going to be saved for next week. You would have a timing violation. That's the word for it. I'll leave it at that because we're going to spend so much time on it next week that you'll be sick and tired of it. Yeah. Okay, great. So yeah, let's assume at this point that the clock is running really slow. It's running much slower than the combinational logic does. Let's assume that for now. Okay. I now have this circuit. So notice that these two flip-flops, how many bits do they store? Right, so I'm assuming that each flip-flop, I'm just going to assume that each of them stores 1 bit. So therefore, yeah, together it's 2 flip-flops, so it stores 2 bits. So let's go through this, but maybe take 1 minute first. I'll let you do it. Maybe try to absorb. If you have any questions about flip-flops, go and chat with the person next to you, and let's reconvene. Try to solve this all the way through. See what you can figure out for this circuit. Okay, this is an OR gate. This is an AND gate. Okay, begin. Oh, and also just assume that there's no delay. Assume everything just takes 0 nanoseconds. Yeah, just propagates immediately. Yeah, okay, begin. Yeah. Okay, let's start going through it. So, okay, starting out, so Q is set to 1, Q0 is set to 1, Q1 is set to 0. You can just see that in this initial state, okay? And then after that, then we have, A is 1, B is 0. So let's look at Q0 first. So what happens at this point right here? So Q0 is being fed by D0, you can imagine. D0 is fed by A or Q1. So at Q0, do we have, let's also just assume that A and B were the previous value as well. Was that your question? No, okay.
No, I was gonna say what I thought it was.
Yes, please.
Is Q0 gonna be 1?
Okay, so why is it 1?
Because A is 1 and the or B, like if 1
Yeah.
is the only answer, then it's yes.
Right, yeah. One or anything is 1. So A is 1, okay, right? So A is 1, so it'll come into here. Yeah, so Q1 will stay 1, okay, good. What is Q1? So Q1 is B and Q0, but B is 0. So therefore, Q1 will be what?
0.
Yep, 0, okay, good. Okay, let's now, the next step of Q1. So Q1 is B and Q0. So if we look, do we have B and Q0? For the next step? Yeah? Yeah, so this is a little bit confusing, right? Because B is very clearly 1 at this step. But remember, we care about what happened last cycle. We care about the D input. So the last cycle, what was the value of B? Yeah, it was actually 0. So therefore, we have 0 for B, and we have 1 for Q0. So therefore, Q1 will stay at 0. Okay, now Q0, what, so we have A or, whatever, I guess, yeah, so we can just see immediately that A on the previous cycle was set to 1. So therefore, Q0, what will the value be for the next cycle? So A was 1 on the previous cycle, so therefore on now this cycle, it will stay 1. Okay, good. Now let's look what happens next. So now A drops to 0, okay, and A is also fed by Q1, and Q1 on the previous cycle was also 0. So we have 0 or 0. So Q1, what happens to Q0? Yeah, Q0 goes to 0. And you know, I actually just realized I'm off a little bit. I'm so sorry, because we need to be looking at the pause edges. I was looking at the neg edge. Sorry about that. Did that change anyone's answers? Are we still okay? Hopefully we're okay. Okay. Good. Yes, so on the previous cycle, we had A is 0 and Q1 is 0. Yep, so let me just fix that. Okay, so that changes now a bit earlier. Okay, and now we have Q1. So Q1 is set by B and Q0. So do we have 1 or 0 for the next cycle? Yeah, it looks like 1, right? Because we have Q0 is 1 and B is 1 in this immediate part right before Q1. So now Q1 goes to 1. Okay, what's the next thing for Q1? So we have B and Q0. Should that be 0 or 1?
0.
Yep, 0. So on the next cycle, now Q1 goes to 0. Okay, and then Q0 is A or Q1. Do we have A or Q1 for the previous cycle? Yes, right? Which one is set? Q1. Yep, thank you. Okay. What is next? So we have A or Q1. What happens for the next cycle of Q0? Yeah, stays 1. Which of the values are 1? Yeah, A. Okay, good. And now Q1. What happens with the next cycle? So we have B and Q0. Yeah, 1. So if we look at just what happened most previously, we see both of these are 1. So this will come back to 1. Good. And then for the next cycle, so now we have B and Q0. What is the next cycle? Yeah. What is it? 0. Okay. Which of these two are 0? Yeah, it's B. So this will fall down because B was 0 right there. Okay. And then finally for Q0, what happens on this next cycle? So Q0 is A or Q1. Yeah, stay 1. Yeah. Questions on this? Okay. Let's go through.
Wait,
Oh.
should Q0 drop on that last rise again?
This one?
Yeah.
Let's double check. So we have A or Q1. And we can see right here that A is at 1.
But the next, right?
Oh, the one you're saying.
Yeah, the very last.
Oh, you're saying right here?
Yeah.
Oh, sure, sorry. I guess I didn't continue it out. Yeah, sure. Okay, so let's do this. So now Q0 takes in 0 or 0. So yeah, so it looks like on this final little bit, it goes to 0. Sure, and then what's Q1 right here? Yeah, so it's B and Q0, so therefore, yeah, B is 0, so it's going to stay 0. Sure, yeah, okay. Cool. That's good. It's a little bit confusing the first time. I feel like the main thing is sometimes it's hard to remember when you're supposed to sample from. So remember, so anytime you have a pause edge, you should imagine that you sample right before that pause edge. So you look at whatever D is right before the pause edge, and that's your new value of Q. So sometimes it can be pretty tempting to look at the value of like Q on the next cycle or like on your current cycle and then use that value. It's very important to look at the previous cycle because the previous cycle is what tells you what to do for the next cycle. Okay. Good. Should we go through another example of this? Okay, I'm getting a lot of nods. So here is the, I guess, yeah, okay. The exact same circuit, I don't like that. Let's do, okay, yeah. Here are 2 AND gates. I know it doesn't quite look like it. Hold on, it's gross. All right, a little bit better. Cool, so these are 2 AND gates. So otherwise it's the same, slightly different inputs. And let's assume that we start out not knowing the values of Q0 and Q1. And let's also extend the inputs to be over here. All right, so let's get started. So starting out, we can see that Q0 and Q1 are unknown. But on the next cycle, we should probably be able to figure out something from them, from these inputs. So, okay, if we have A and B starting as 1, then, sorry, I guess A is 1, B is 0. So let's look at Q1 first. So if B is 0 for this whole input, then what will the output of this AND gate be? Yeah, just no matter what, since B is 0. So therefore, on the next cycle, Q1 will very clearly be B0, right? So good. So this next clock cycle, so this is all 0. Okay. Then for Q0, so what about for this? So A is currently 1, so therefore we need to look at what Q1 is. So what should be the output of this AND gate? So if we look at the previous clock cycle, so this whole period right here, what is the value of Q1? Unknown. Okay, so cool. So therefore, we know what the value is. It is unknown. All right, cool. Next cycle. So Q0, let's look at this again. So now we have A and Q1. So what is the previous value of A? Yep, 0 goes to 0 for just like a little bit right before the pause edge. Okay, so therefore, no matter what, Q0 is going to be what?
0.
Yeah, exactly. So Q0 is going to be 0, so it goes to 0. Yeah, and then Q1 now, well, Q1 is taking Q0 and B. So what is B?
1.
Yeah, B is 1. Okay. So B and Q0. What is Q0?
0.
Unknown. Yeah, okay. So therefore, Q1 is going to be what? Yeah, it's going to be unknown. So that's interesting. Okay. Sure. Let's look at the next value of Q1. So Q1 is B and Q0. What is the previous value of Q0? 0. Okay, so what will Q1 be?
0.
Yeah, it'll be 0. Okay, and then Q0 is A and Q1. What is A? 0. Okay, so this will be now 0. So now both of these are 0. And I'm pretty sure no matter what happens now, we will just always stay 0 for the rest of this. Right? Yeah. So why this part? Yeah. So if we look back at this again, so we were so Q0 is A and Q1. So when you take A and Q1, so A was 1, but Q1 was unknown. So if we do like 1 and an unknown value, then we don't know what the output will be. Because if the unknown value was 0, then it will be 0. But if the unknown value is 1, then it will be 1. So yes, so it relies on the on whatever state this unknown Q1 was in. Yeah. Okay. Cool. Yeah. Makes sense. A little bit mean to use unknown values. Maybe would have made more sense if I had put like a 1, and then you could see the 1 like propagating and oscillating between these two flip-flops. Yeah, if I think if Q1 was 1, then it would have gone into Q0, then it would have gone back into Q1. So that's what would have happened if Q1 had started at 1. Yeah. Okay. Questions? Is it okay? All right. A little bit, yeah, maybe not quite what you were expecting. Okay. Should we do one more of this? Or are you feeling pretty confident to learn a new thing? Feeling good? Can I get a thumbs up if you want to do this example? Thumbs down if you're tired of this and want to move on. All right, I think it's exactly 50-50. I'll move on just because we're going to be spending the next like 2 weeks on this anyways. So I think you'll kind of pick it up as we go. This will be on your homework 2, which I will post this weekend at some point. Okay. So I'm going to move on. So this was a very interesting kind of case, right? So we have unknown values. This happens all the time when you plug in your CPU or you plug in your circuit, and you don't actually know what is initially stored in all of your flip-flops. That is a fact. You don't know what is going to be stored in your flip-flops. Depending on how old the flip-flop is, it may have degraded to where some of the flip-flops store 1s, some of the flip-flops store 0s. There's no way that you can actually 100% store initialize your circuit with a known value. So therefore, we need to figure out some way to make sure that our circuit somehow enters a known state. So right now, we're in an unknown state, and we figured out that there is some sort of path that would have gotten us to this known state where we know all of our flip-flop values. But there's not too much time anyways. But I'll keep just finishing this thought. So the additional functionality that every flip-flop has is every flip-flop also has a reset input. And this is something that I left off of this diagram, so I can scroll back up. So this flip-flop up here will actually have another input, reset, and we'll make it right here, reset. And when you set this value to 1, then this will reset the value of the flip-flop to some desired output. Usually you just reset the flip-flop to 0, although you can have flip-flops that reset to 1. Yes, so keep that in mind. We will talk about the different types of reset on Monday. Was there a question?
Is the reset dependent on the clock at all, or does it do it like that?
So the reset, there are 2 types of resets. So ones that do rely on the clock, and then some resets do not rely on the clock. And we will talk about those differences. Any other questions? Okay. Question. There's not attendance today. Okay. Thank you, everyone. Enjoy your weekend. I will see you on Monday.